Okay guys, so in the last video I have talked about the basic concept behind bending moment and shear force, and in this video I will talk about the relation between this shear force and bending moment. Okay, so in the last video we have also solved a simple problem, and there we have taken a simply supported beam and it was subjected to some point load like this, and we have tried to find out the equation for shear force at any section at a distance of x. Okay, so before discussing about the relation between shear force and bending moment, let's solve another problem. And in this case, let's say we have a simply supported beam like this. Okay, and this is, let's say, support A and support B. Okay, we are just drawing directly the free body diagram. That's why I am not showing here the support. Here I am showing the reaction. Okay, and let's say it is subjected to an UDL, okay, with magnitude W per unit length. Now you may ask me, what is UDL? UDL is nothing but a distributed load. Here you can see that the load has been applied at a particular point. Okay, let's say this load was W, capital W, and here we have small w, and if the total length of this beam, let's say for example this is L. Okay, so what is the total load acting on this beam? This is W times L, and it is acting at the CG or at L by 2 from any support. Okay, this is the total load. This is the concept of UDL. Okay, now first we will find the equation for bending moment and shear force at any section at a distance of, let's say, x. Okay, at a distance of x from A, we have to find out the equation for bending moment and shear force. So before that, what we have to do, we have to simply find the reaction, and from symmetry you can also find out from this static equation, that is fx is equal to 0, fy is equal to 0. Okay, so here reaction Ra and reaction Rb, this is equals with WL by 2, WL by 2. Okay, because the total load is WL, and from symmetry you can find out the reaction. Also, if you use this equation, in that case also you will find the same reaction. Please do it yourself to brush up your concept. Okay, so now the very first task was to find out the shear force at any section at a distance of x from any support. Here what we have to do, we have to simply separate out the left portion. You can also separate out the right portion also. So this left portion looks something like this. Okay, this is the beam, we have taken it out. This is the section. Okay, and here what are the forces? So the reaction force is acting like this. Here this is WL by 2, and the part of the UDL is also acting like this. Okay, and this is for at a distance of x. Okay, so what is the total magnitude of this UDL? This is W times x, and it is acting at the CG here. Okay, what is this distance? X by 2. Clear? So now you have seen that at this section, well, first make this section red one because we have cut it, that's why it is bleeding, and we have total 3 force here. First one was, please repeat with me, yes, axial force NX. Second one was, yes, it was shear force, okay, Vx, and third one was, yes, moment, Mx. Okay, but now here you can see there is no such horizontal force. Okay, all the forces are vertical one. For example, this reaction is acting vertically. Okay, also this resultant UDL is also acting vertically downward. So there is no horizontal force. So you can simply ignore this component nx. So we have two unknown, Vx and mx. Okay, to find the Vx, what we have to do, we have to use the static equation of static equilibrium, because this whole system is in equilibrium. So there is no upward or downward movement. So total net force acting in vertical direction, that is summation of Fy, is equals with 0. And if we consider the upward as positive, we can write that WL by 2. Okay, let me use some different color. WL by 2 positive. Okay, and we have a downward UDL, that is negative, and it is Wx. Okay, this is equals with 0. No, we have not considered this Vx. This is upward, so we have to consider this one also, and it is plus Vx. Now it is equals with 0. So we need Vx. So keep Vx at the left portion, left side, and we are getting Vx as simply Wx minus WL by 2. Okay, so we have got the equation for shear force at a distance of x from support A. First equation, got it. Now second one, to find out the moment, what we have to do, we have to take the moment about this point, because it is not rotating. So net moment about this point indicated in green color is 0. Okay, so summation of moment about, let's say this is point O is equals to 0, and we are considering everything clockwise as positive. Okay, and this gives us simply what is the moment due to this WL by 2. Okay, this is clockwise about this point O, so plus WL by 2 times x. Okay, what is the moment due to this Wx or resultant UDL Wx, the load Wx into distance acting at a distance of x by 2, and it is creating anti-clockwise. Okay, acting downward, here is the point, so it is creating some anti-clockwise rotation, so negative. Okay, and we have taken mx as positive. This is our assumption, we may be wrong. So plus mx, it is equals with 0, and now you are getting mx as simply 1 by 1 Wx square by 2, okay, minus WL times x by 2. Okay, got it. So here you can see that this function is a quadratic equation. This equation is a quadratic equation because there is x square here. So you have got both the equation for shear force as well as bending moment. Okay, now I think it is completely clear to you how to find the shear force as well as the bending moment for any given type of loading. Okay, so now it's time for finding the relation between these two friends. Okay, shear force and bending moment. So before that, let me clear everything. Okay, so it's all clear. Now again we will consider the beam. Okay, this was our beam, and just now you have find out the reaction. Okay, and it was subjected to some UDL. Okay, and the magnitude of this UDL was small w. Okay, per unit length. Okay, now your task is to cut two section. Okay, let's say we are cutting at a distance of x, okay, a section like this. Not only that, I am also requesting you to cut another section at a distance of dx from this section. This was our first section. Let's say this was mn, okay, this is dx. We are cutting another section. Let's say this is m dashed n dashed, okay. Now I am asking you to just separate it out, okay. So we are separating it out like this, okay, and the section is looking like this. This is the beam section. We have simply cut it out from the main beam, and this left side was your mn, right side was, sorry, this was m and this was your n. It is m dashed, this is n dashed, okay, and the width is coming as dx, okay. So the very first thing, you will be able to find the shear force as well as the bending moment at this section. No issue, you have just find it out at a distance of x. You can do it. Yes, let's say this is simply the shear force is acting like this, and this is, let's say, bx, okay, and the bending moment is acting, let's say, like this, okay. The bending moment is acting like this. This is, let's say, mx, and in this part we have some UDL acting like this one, okay. This is the W, and total load is W times dx, because the length is dx, okay. And similarly, you can also find out the shear force in this section. Let's say that is, we are considering it as downward, and it is Vx plus very infinitesimal increment, that is dvx, okay. And also, let's say here the moment is acting, this one is the moment acting like this, and it is also mx plus the increment, that is dmx, okay. And we are considering this point as our reference, okay. Now this whole beam, this whole system is in equilibrium, static equilibrium, agree. So of course this part is also in static equilibrium, agree. So there is no vertical movement, so the net force acting towards vertical direction is 0, okay. And also there is no resultant moment or rotation of this element. That is why the net moment about this point is also 0. So this is summation of moment about point O, let's say this is O, okay, is also 0. Now sign convention is, we are considering everything is upward as positive, and everything is clockwise, that is positive, okay. So first thing first, the vertical forces from left side, Vx upward, so plus Vx, okay. Let me draw this in the same color, okay, that is Vx. And here this UDL is acting downward, here resultant is acting downward, and it is negative, that is W times dx, okay, because W is per unit length and the total length is dx, here this one. And the left one, that is again in this color, it is acting downward, so Vx minus dvx is equals to 0. So from this cancel vx, and we are getting that dvx, okay, is equals with minus w dx, or we can rewrite it as, okay, some uniform color, that is dvx by dx, or the change of shear force is equals with minus w. Okay, so this is first equation. Change of shear force is completely related to the magnitude of UDL. Okay, now come to the moment equation, and here we are taking moment about this point. Okay, so start from the left. First this one, it is clockwise, so plus mx. Okay, then come to the shear force, this one, about this point the moment is clockwise, so vx time dx, distance is dx. Now about the UDL, okay, this is creating some anti-clock rotation, so minus w times dx, and it is acting at a distance of dx by 2. Okay, so dx by 2, clear. And finally this vx into vx plus dvx, actually this is passing through this point, so it will have no moment. And finally this one, okay, it is anti-clockwise, so minus mx minus bmx, this is equals to 0. Okay, and here we have to do some approximation. Here dx is almost tends to 0, so of course we can ignore the higher power of dx square, so this is almost equals to 0. Okay, cancel mx, and we are getting from this equation, okay, we are getting v dx, again make some uniform color, vx dx is equals with dmx, or we can rewrite it as dmx dx equals to vx. Okay, so we have derived both the equation. So before discussing further, let me clear all the bullshits. Okay, so from this element you have got two relation, first relation and second relation. Okay, now let's say we don't have any UDL. Okay, so in that case, let's say this is the beam and we have only a point load. Okay, so here the dvx dx will be simply 0 for all this portion. Okay, got it? Because there is no such forces. That means in this location the shear force is constant. Okay, agree? And if dv dx is 0, in that case we are getting dm dx as, what is that? Simply put the, this is constant, okay, this is constant, dx is constant, so dmx dx is become constant. Okay, there the slope of the bending moment diagram becomes constant. Yes, very new term, that is bending moment diagram. So similarly, this one, if we plot this shear force, becomes like this, and this is known as shear force diagram. Okay, it's already 20 minutes. We'll discuss this bending moment diagram and shear force diagram in the next video. That's it.